Today we're going to be talking about the ways in which we can write out chemical formulas and how to convert from one way to another. Let's see how we do that. Okay, so in this video we're going to be going over two ways in which we can write out chemical formulas. The first way is known as a molecular formula, and this indicates the total number of atoms of each element present in a compound. Now this type of formula is the formula you're most likely to see when you learn about chemical formulas in chemistry, because it indicates the actual number of atoms of each element present in a compound. However, there is another way in which a chemical formula can be written out, and this is known as an empirical formula, and this is the simplest ratio between atoms of different elements in a compound. So essentially, it's the simplified version of the chemical formula in which the numbers, the subscripts within the chemical formula, are as low as they can possibly be. Let's see how we can convert from a molecular formula to an empirical formula. Okay, so what we have here are two molecular formulas for two different compounds. And what we have to do is you have to consider what is the highest number that the numbers in the molecular formula can be divided by to lead to a whole number, i.e. the highest common factor for all the numbers in the molecular formula. So let's take this one for instance. C6H12O6. So 6, 12 and 6. What is the highest number that those three numbers can be divided by leading to a whole number? And the answer is 6. So therefore, the number that we must divide these three numbers individually by is 6. So to do that, we can now draw an arrow, and we're going to say we're going to divide it by 6. So for carbon, 6 divided by 6 is 1. So we're going to write C. And because there's only 1, we're only going to write the symbol for carbon. We're not going to write 1. Hydrogen, 12 divided by 6 is 2. So we write H for hydrogen and a 2. And then for oxygen, 6 divided by 6 again is 1, so O. And there we have the empirical formula for this compound, which is glucose. Okay, let's now do another one. So in this molecular formula, we have 5 carbon, 8 hydrogen, and 4 oxygen. Now, I've put this molecular formula in this exercise because this is the kind of trick question you may get in an exam or a test. Because if you notice, 5 is a prime number, which means that it can only be divided by either 1 or itself, which is 5. So unless the other two numbers can be divided by 5, which in this case they can't without leading to a decimal, and we don't want a decimal, because 8 divided by 5 doesn't lead to a whole number, 4 divided by 5 doesn't lead to a whole number. So as a result, the only number that those three numbers can be divided by is 1. And as a result, the empirical formula for this compound is actually the same as the molecular formula for this compound. Now this compound is glutaric acid, and as I said before, I've included this as an example in this exercise because you may be asked to supposedly convert from a molecular formula to an empirical formula for a compound in an exam or test, and in actual fact the empirical formula would be the same as the molecular formula. And this is sort of a question that's sort of included in a test and an exam to really test to see if you know when to apply this process and essentially when not to apply this process. Okay, so now we know how to convert from a molecular formula to an empirical formula when we know what the molecular formula of a compound is. Let's consider the situation where we are asked to work out the empirical formula of a compound, but instead of being given the molecular formula for the compound, we are instead given the percent composition for the compound. Now what this refers to is that we are given the percentages of the elements by mass that are present in the compound. Let's have a look at this question. A compound contains 11.2% of hydrogen and 88.8% of oxygen. What is its empirical formula? So the first thing we have to do is we have to convert those percentage figures we are given in the question into masses in grams. So, to do that, because the percentage figures add up to 100%, all we have to do is change the unit from percent to grams. So we have 11.2% of hydrogen, which means we have 11.2 grams of hydrogen, and we have 88.8% of oxygen, which means we have 88.8 grams of oxygen. Next, we have to convert those masses in grams into moles. And to do that, we must multiply the mass of each element by a conversion factor that consists of the molar mass of the element and an equivalent value, which is the 1 mole of that element, because the mole mass is the mass of 1 mole of substance. So for hydrogen, we take the mass of the element in this question, which is 11.2 grams, and we multiply it by a conversion factor that consists of 1 mole of hydrogen divided by the molar mass of hydrogen, which is 1.01 grams of hydrogen. We cancel out the unit of grams of hydrogen and we are left with an answer to three significant figures of 11.1 moles of hydrogen. For oxygen, we have 88.8 grams of oxygen. We cancel the unit of grams of oxygen. We carry out the calculation 88.8 times 1 divided by 16.0 and we get an answer to three significant figures of 5.55 moles of oxygen. Next, we divide the answers we had in the previous step by the smallest number of moles we had in our answers to the previous step. And we do this for each element. So for hydrogen, we divide 11.1 moles by 5.55 moles and we get an answer of 2. And for oxygen, we have 5.55 moles and we divide it by 5.55 moles and we get an answer of 1. Now these answers don't have any units because these are the numbers we are now going to include as subscripts in our empirical formula for this compound. And now for the final step for this question, we now write the answers to step 3 as subscripts in the empirical formula. So for hydrogen we had 2, so we write the chemical symbol for hydrogen, which is H, followed by the subscript of 2. And then for oxygen we had 1, so we just write the chemical symbol for oxygen, as we don't write 1s in chemical formulas. And we get an empirical formula for this compound of H2O, which is for the compound of water. And once again this illustrates how an empirical formula can be the same as the molecular formula for a compound. Okay, so now we know how to go from a molecular formula to an empirical formula. Let's now go from an empirical formula to a molecular formula. Now the first thing to note about an empirical formula is that it can represent numerous compounds, which means it can represent numerous molecular formulas. So in order to work out which molecular formula an empirical formula is representing, we need a bit more information. And that information comes in the form of the molar mass of the molecular formula. So let's have a look at this question. What is the molecular formula of a compound with a molar mass of 42.06 grams per mole and an empirical formula of CH2? So what do we do with this information? Well, we divide the molar mass of the molecular formula by the molar mass of the empirical formula. So in this question that would be 42.06 grams per mole divided by a molar mass of 14.02 grams per mole and we get an answer 3. Okay, so now what do we do with this information we got from this part of the question? Well, we're now going to multiply the subscripts in the empirical formula by 3 in order to work out what the subscripts in the molecular formula are. So, in the empirical formula we have 1 carbon multiplied by 3, which means we have 3 carbon in the molecular formula, and we have 2 hydrogen in the empirical formula multiplied by 3, which means we have 6 hydrogens in the molecular formula. So the molecular formula for this compound is C3H6, which is the molecular formula for propene or propylene. Okay, so let's now work out the molecular formula for a compound when we're given the molar mass of that compound, but instead of being given the empirical formula, we're given the percent composition. Imbilaferone, which is a compound that's found in sunscreen, has a molar mass of 162.06 grams per mole and a composition of 66.64% carbon, 3.74% hydrogen and 29.62% of oxygen. What is its molecular formula? So the first thing we have to do is work out what the empirical formula for imbilaferone is. And the first step in this process is to convert the percentage figures we have in the question into grams. Now once again, as was the case earlier on in the video, the percentage figures add up to 100%. So this is simply a matter of changing the unit from percentage to grams. So for carbon, we have 66.64% of carbon, which means we have 66.64 grams of carbon. We have 3.74% of hydrogen, which means we have 3.74 grams of hydrogen. And we have 29.62% of oxygen, which means we have 29.62 grams of oxygen. Next, we have to convert the mass of each element in grams into moles. So for carbon, that would be 66.64 grams of carbon, times 1 mole of carbon divided by 12.0 grams of carbon, and then we cancel out the unit of grams of carbon, and we get an answer to 3 sig figs of 5.55 moles of carbon. For hydrogen, we have 3.74 grams of hydrogen, times by 1 mole of hydrogen, divided by 1.01 grams of hydrogen, cancel the unit of grams of hydrogen, and we get an answer to 3 sig figs of 3.70 moles of hydrogen. And then for oxygen, 29.62 grams of oxygen, times by 1 mole of oxygen, divided by 16.0 grams of oxygen, cancel the unit of grams of oxygen, and we get an answer to 3 sig figs of 1.85 moles of oxygen. We then have to divide the answers that we had in the previous step to this question by the smallest number of moles that we had in our answers to the previous step to the question. So for carbon, that would be 5.55 moles divided by the smallest number of moles we had in the previous question, which was 1.85 moles, and we get an answer of 3. For hydrogen, it's 3.70 moles divided by 1.85 moles, and we get an answer of 2. And then for oxygen, 1.85 moles divided by 1.85 moles, and we get an answer of 1. Now these answers don't have any units, because these are the numbers that are now going to be the subscripts in the empirical formula for this compound. Okay, so now we can write out the empirical formula for this compound. So we have 3 carbon, 2 hydrogen and 1 oxygen. So now we can now carry out the next step in which we divide the molar mass of the molecular formula by the molar mass of the empirical formula, because we can now work out that the molar mass of the empirical formula is 54.02 grams, and we are given the molar mass of the molecular formula, 162.06 grams in the question. So now we can divide these two values and we get an answer of 3. And it is this answer to this part of the question that we're now going to multiply the subscripts in the empirical formula by in order to work out what the subscripts are in the molecular formula. So now we can multiply the subscripts in the empirical formula by 3. So we have 3 carbon in the empirical formula, which means in the molecular formula we have 9 carbons. In the empirical formula we have 2 hydrogens, which means we have 6 hydrogens in the molecular formula. And in the empirical formula we have 1 oxygen, which means we have 3 oxygens in the molecular formula. So the molecular formula for imbilaferone is C9H6O3. So there you go guys, that's how we can convert from the molecular formula for a compound to the empirical formula for a compound, and vice versa. I hope you enjoyed this video and found it helpful. If you did, please give it a thumbs up and don't forget to subscribe to the channel. If you want to see some more science tutorials, please check out my blog, link to which I'll leave down below. And if you want to follow me on Twitter, Instagram, I'll leave links to those down below as well. Thank you for watching, and I'll see you next time.